In our last video, we explored what a function really is, a precise relationship between inputs and outputs. We saw that functions don't need formulas, they just need unambiguous rules. And crucially, we discovered that a function can approach a limit at a value where it doesn't even exist. That last insight, that functions can have limiting behavior at points where they're undefined, is about to become absolutely essential. Because today, we're going to face a problem that stopped mathematicians for 2,000 years. By the end of this video, you'll understand why the most natural question in physics, how fast am I going right now, leads to mathematical meaninglessness, and how that impossibility becomes the foundation for all of calculus. Let's start with something completely familiar. You're driving from San Francisco to Los Angeles, a distance of about 380 miles. The journey takes you 6 hours. How fast were you traveling? This is trivial. Divide distance by time. About 63 miles per hour. Simple arithmetic. But let's be precise about what this number actually means. This average speed of 63 miles per hour doesn't tell you what happened during your journey. You could have driven at exactly 63 miles per hour the entire time. Or you could have been stuck in traffic for 3 hours, then sped along at 126 miles per hour for the remaining 3 hours. Both journeys have the same average speed, but they're completely different experiences. The average washes out all the details. Let's formalize this. Suppose an object travels from position S1 to position S2. And this takes time from t1 to t2. The average speed over this time interval is simply the change in position divided by the change in time. This Greek letter delta represents change. We'll see it everywhere in calculus. And this formula is perfectly rigorous, perfectly clear, and perfectly useful, as long as we're asking about average speed over some time interval. But now comes the question that changes everything. You're driving down the road, and you glance at your speedometer. It reads 80 miles per hour. What does this number mean? And here's the critical question. What does it mean to say you're going 80 miles per hour right now, at this exact instant? Let's try to use our formula for average speed, but apply it to a single instant. We'll call this instant t. At time t, you're at position s of t. To find your speed at this instant, we need another instant. But there is no other instant. We're asking about the speed now. Let's push forward anyway. If we use time t for both the start and end point, 0 divided by 0, this is not just undefined, it's meaningless. It could equal anything or nothing. We've hit a wall. This isn't a technical difficulty we can clever our way around with better algebra. This is a fundamental conceptual problem. The ancient Greeks knew about this. Medieval mathematicians wrestled with it. And for 2,000 years, nobody could solve it. Because the question itself seems to contain a contradiction. Motion happens over time. It requires a beginning and an end. But an instant has no duration. No time passes, nothing moves.
At any single instant, an object isn't going anywhere. It's just there, frozen at a position. So what could instantaneous speed possibly mean? Speed requires motion. Motion requires time. An instant has no time. So what is instantaneous speed? Let's pause and consolidate what we know. We have two completely different situations. Average speed works perfectly. Instantaneous speed seems impossible. And yet, your speedometer exists. It shows you a number, right now, at this instant. Physics works. Cars brake in time. Missiles hit their targets. The universe operates as if instantaneous speed is a perfectly meaningful concept. So the question isn't whether instantaneous speed exists. Clearly it does, somehow. The question is, how do we make mathematical sense of something that seems logically impossible? And that's where one of the most beautiful ideas in all of mathematics comes in. Here's the key insight. Even though we can't calculate speed at an instant, we can calculate speed near an instant. And if we get closer and closer, maybe, just maybe, we can figure out what the speed is approaching. Let's say we want to know the instantaneous speed at time t. We can't use time t for both endpoints, but we can use time t as one endpoint and another time, call it t plus h, as the other endpoint. This h represents a small time interval. Not 0, that would bring back our problem, but small. And we can calculate the average speed over this interval. Now here's what changes everything. Watch what happens as we make h smaller and smaller. With h equals 1 hour, we get an average speed over a long interval. With h equals 10 minutes, the interval is shorter, and the average speed might be different. With h equals 1 second, we're getting very close to our instant t. The average speeds are changing, but notice, they seem to be stabilizing. They're approaching a specific value. And this is the breakthrough. We don't set h equal to 0. That still gives us 0 over 0, which is meaningless. Instead, we ask,
What value is the average speed approaching as h gets closer and closer to 0? This is not 0 over 0. This is the limit as h approaches 0. The value that the average speeds are tending toward without h ever actually reaching 0. Remember from our last video, a function can have a limit at a point where it doesn't exist. That insight is exactly what saves us here. The fraction s of t plus h minus s of t over h doesn't exist when h equals 0, but it can still approach a definite value as h approaches 0. Let's see this geometrically because the picture makes it crystal clear. When h is some finite value, the quotient s of t plus h minus s of t over h represents the average speed over the interval from t to t plus h. Geometrically, this is the slope of the line connecting these 2 points. We call this a secant line. Now, watch carefully as h gets smaller. As h approaches 0, the second point slides along the curve toward the first point. The secant line rotates into a limiting position, and this limiting line is called the tangent line to the curve at time t. The instantaneous speed at time t is the slope of this tangent line, and that slope is the limit we wrote down. This is why calculus works. The limit transforms the meaningless 0 over 0 into the perfectly meaningful slope of a tangent line. Let's make this concrete with a simple example. Suppose the position of an object is given by s of t equals t squared. This means at time t equals 1, the position is s of 1 equals 1. At time t equals 2, position is s of 2 equals 4. At time t equals 3, position is s of 3 equals 9, and so on. Question: what is the instantaneous speed at time t equals 2? We use our formula. The instantaneous speed at t equals 2 is the limit as h approaches 0 of s of 2 plus h minus s of 2 over h. Now we substitute s of t equals t squared. So s of 2 plus h equals open parenthesis 2 plus h close parenthesis squared, and s of 2 equals 4. Let's expand that square. Open parenthesis 2 plus h close parenthesis squared equals 4 plus 4h plus h squared. The 4's cancel. Now minus, and this is crucial, we can factor out an h from the numerator. Since h is approaching 0 but never equals 0, we can cancel the h in numerator and denominator. We're left with the limit of 4 plus h as h approaches 0. The instantaneous speed at t equals 2 is 4. Not 0 over 0. Not undefined. 4. We can verify this geometrically. At the point 2, 4 on our parabola, we draw the tangent line. The slope of this tangent line, which you can measure, is indeed 4. The algebra and the geometry agree perfectly. Now let's step back and see what we've really accomplished. We started with an impossible question: what is instantaneous speed? And we solved it by changing the question slightly. This idea, replacing a direct calculation with a limiting process, is so powerful that we give it a name. When we take the limit of f of x plus h minus f of x over h as h approaches 0, we call this the derivative of the function f at the point x. The derivative is incredibly rich in meaning. Depending on what your function represents, the derivative tells you, if f represents position, then f prime represents velocity. If f represents velocity, then f prime represents acceleration. If f represents any quantity, then f prime represents its rate of change. The derivative is the mathematical formalization of the concept of instantaneous rate of change. And that's why calculus is so universally applicable, because change is everywhere. Look at what we've constructed. We started with average rates of change, simple division. Then we faced the paradox of instantaneous rates, which seem to require 0 over 0. And we resolved it using limits, the idea that a function can approach a value even where it's not defined. This is why we spent our first video on functions and limits. Without understanding that the limit of f of x as x approaches c can exist even when f of c doesn't, we couldn't make sense of the derivative. It would just look like meaningless manipulation of 0 over 0. Let's consolidate everything we've learned today. Average speed over an interval is straightforward, delta s over delta t. Instantaneous speed at a single moment leads to 0 over 0, meaningless. The solution? Take the limit of average speeds as the interval shrinks. This limiting process, the derivative, is how we make precise the concept of instantaneous rate of change. The derivative resolves a 2,000-year-old paradox. It shows us that instantaneous speed isn't found by direct calculation at a single point. It's found by examining behavior in neighborhoods around that point and taking a limit. In our next video, we'll develop the formal machinery of derivatives, the rules and techniques that let us calculate them efficiently without going through the limit process every time. But you'll always know where those rules come from. For now, understand this. You've just learned one of the deepest ideas in mathematics. The derivative isn't just a calculational tool. It's a conceptual breakthrough about how to make precise the notion of instantaneous change. And that changes everything. Thanks for watching. In the next video, we'll see how this idea unlocks an entire world of applications. Subscribe so you don't miss the next episode.